Imagine throwing a ball into the air. What happens? It goes up, slows down, stops for a split second, and then falls right back into your hands. That's because Earth's gravity pulls it back. The ball is trapped. It's bound to Earth. Now imagine throwing that ball so hard, so incredibly fast, that it never comes back. It just keeps going up and up and up, sailing past the clouds, past the atmosphere, past the moon, and off into space forever. That ball just escaped. It's free. It's never returning. This is the fundamental difference between a visitor and a resident in space. And 3I Atlas, the third confirmed interstellar interloper to pass through our solar system, is giving us the most dramatic cosmic lesson in the mathematics of goodbye. Let's talk about orbits. Every object moving through space follows a path determined by gravity and speed. If you're moving slowly enough, gravity wins, and you're trapped in an ellipse, like planets circling the sun. Your path is a closed loop. You're coming back. Maybe it takes a year, maybe a million years, but mathematically you're guaranteed to return. We call this eccentricity, less than one. Think of it as gravity's invisible leash keeping you on a cosmic loop. But if you're moving fast enough, something extraordinary happens. Your path becomes a hyperbola, a curve that never closes, a line that stretches off into infinity and never circles back. Your eccentricity is greater than one. You've broken free. You're not a resident anymore. You're a visitor passing through. And that's exactly what 3IATLAS is. A messenger from another star system, carrying an eccentricity of approximately 6.1374. Let that number sink in. 6.1374. That's not just slightly hyperbolic. That's dramatically, spectacularly, undeniably hyperbolic. It's one of the most energetically unbound objects ever observed passing through our cosmic neighborhood. This comet isn't just leaving our solar system. It's rocketing away with such tremendous speed that the sun's gravity barely even bent its path. Think about escape velocity. Near Earth's orbit, about 93 million miles from the sun, you need to be moving at least 42 kilometers every single second to escape the sun's gravitational grip forever. That's over 94,000 miles per hour, faster than anything we've ever built. But 3IATLAS, it was moving at 68.3 kilometers per second at its closest approach to the sun. That's more than 60% faster than the escape threshold. This visitor brought its own speed from beyond our system, a hyperbolic excess velocity of nearly 58 kilometers per second, a signature proving it was violently ejected from its birth star system. Compare that to its predecessors. The first interstellar visitor, the mysterious one Oumuamua discovered in 2017, had an eccentricity of only about 1.2. It was barely hyperbolic, suggesting it drifted away gently from its home system. The second visitor, 2I Borisov in 2019, showed an eccentricity of 3.36, indicating a stronger ejection, probably kicked out by a massive planet. But 3IATLAS, with an eccentricity over 6, that screams violence. Maybe it passed too close to a giant planet and got flung out like a slingshot. Maybe it was born in a chaotic, dynamically hot stellar environment where stars and planets scatter objects with tremendous force. Here's the poetry and the mathematics. Every object with eccentricity greater than 1 is writing the same message across space. I'm not from here. I was born somewhere else under a different sun. I'm just passing through your neighborhood on my way to forever. It's a trajectory that's a cosmic farewell, a geometry that guarantees departure. 3i Atlas arrived from the vast darkness between stars, curved briefly around our sun, and is now sailing back out into the galaxy, never to return. Its path is an open curve, a line that never closes, a comet that will never circle back. And in that trajectory, written in pure mathematics, is the most definitive statement any celestial object can make. I am not one of yours. I am a traveller. I am a messenger from beyond. The numbers don't lie. The eccentricity of 6.14 is an absolute fingerprint. This is a visitor. This is an interloper. This is 3i Atlas, the hyperbolic messenger, carrying the geometry of farewell burned into its very motion through space. And now we know. When we see that number, when we calculate that trajectory, we're not just measuring speed and direction. We're reading a cosmic signature that says clearly and definitively this object was born under another star. But before 3i Atlas arrived at our doorstep, with that spectacular hyperbolic trajectory, it spent an unimaginably long time travelling through the emptiness between stars. And here's what most people don't realise. Space isn't actually empty. Think about the journey. This comet was ejected from its home star system millions, possibly billions of years ago. It's been drifting through the galaxy ever since, crossing distances so vast that light itself takes years to span them. During that entire journey, 3IA TLAS was exposed to something we call the interstellar medium. And that medium, even though it's thinner than anything we can imagine, slowly and relentlessly changed the comet's very chemistry. Let's talk about what space is really like between the stars. We call it a void, but it's more accurate to call it a whisper-thin fog. The interstellar medium is made mostly of hydrogen, about 75%, with helium making up another 25%, plus tiny amounts of dust particles. How thin is it? About 1 atom per cubic centimetre. That sounds like nothing, right? The air you're breathing right now has over 30 billion trillion times more atoms in the same volume. Space is almost incomprehensibly empty. But here's the thing. When you're travelling for millions of years across billions of miles, even that whisper-thin fog adds up. It's like walking through the lightest mist imaginable. One droplet won't make you wet, but walk through it for hours, and eventually you'll be soaked. 3i Atlas walked through that cosmic mist, not for hours, but for eons. The real transformation came from something even more invisible, cosmic rays. These aren't rays of light. They're high-energy particles, mostly protons, that zip through space at nearly the speed of light. They're created by exploding stars, by supermassive black holes, by the most violent events in the universe, and they're everywhere. Right now, cosmic rays are passing through your body, through the earth, through everything. Most of them do nothing. But on a frozen comet drifting through deep space with no atmosphere to protect it, they're sculptors, carving away at the ice molecule by molecule. This process is called radiolysis. Imagine you have a block of ice made of simple molecules like water and carbon monoxide. Now, bombard that ice with high-energy particles for 1 billion years. The cosmic rays smash into the molecules, breaking them apart and reassembling them into new compounds. Simple carbon monoxide transforms into carbon dioxide. Organic compounds form, creating complex tar-like substances. The surface darkens, building up a thick, dark crust of processed material, and that's exactly what happened to 3IATLAS. Scientists studying this comet discovered something extraordinary. Its atmosphere, that cloud of gas surrounding it, contains 7.6 times more carbon dioxide compared to water than typical solar system comets. That ratio is 4.5 standard deviations above normal. In scientific terms, that's shockingly unusual. It's like measuring people's heights and finding someone who's 15 feet tall. It doesn't happen by accident. This extreme carbon dioxide enrichment is the smoking gun. It proves that cosmic rays process the outer layers of 3I Atlas for billions of years, converting the original ices into something fundamentally different. Models suggest this radiation-damaged zone extends 15 to 20 meters deep into the comet's body. That's as deep as a 6-story building is tall. The entire outer shell of this comet has been chemically transformed by its long galactic journey. Think of 3IATLAS as wearing cosmic armor. The tar-like crust created by billions of years of radiation acts as an insulator, protecting the interior from the sun's heat. But it also means that when we observe this comet, we're not seeing its original composition. We're seeing what galactic space did to it. We're reading a record written in chemistry, a diary of endurance through erosion. This revelation changes everything about how we interpret interstellar visitors. When astronomers analyze the gas coming off these objects, they're not learning what the comet's home star system was like. They're learning what billions of years of wandering through the galaxy does to ice and rock. The comet's surface is a history book, and every page has been rewritten by cosmic rays. The resilience is breathtaking. For eons, high-energy particles bombarded this frozen traveler. Slowly, relentlessly, they tore apart molecules and rebuilt them. They darkened the surface, enriched the carbon dioxide, created organic compounds. And through it all, 3I Atlas endured. It survived the erosion, built its protective crust, and kept sailing through the darkness between stars. Now, after its impossibly long journey, it's finally passing through our solar system, carrying that dark armor as proof of where it's been. When we look at 3IATLAS, we're not just seeing a comet, we're seeing the physical evidence of endurance, written in chemistry, shaped by radiation, transformed by time itself. This is what it means to travel between the stars. This is what the galaxy does to wanderers. This is the price and the proof of an interstellar voyage. So 3I Atlas arrived carrying that dark, radiation-damaged crust, a record of billions of years wandering through galactic space. And when it finally swung around our sun, astronomers had one precious chance to study it. They pointed the most powerful telescopes humanity has ever built at this visitor, hoping to decode its secrets. Their primary tool? Spectroscopy. Or, as you might think of it, listening to the colour of starlight. Let's talk about how we actually study comets. You can't touch them. You can't send a probe fast enough to catch up to something moving at 68 kilometers per second. All you have is light. The comet reflects sunlight, and more importantly, it gives off its own light when the sun heats it up and gases start escaping from its surface. Those gases glow with specific colours, and those colours tell stories. Here's the beautiful part. Every element, every molecule, has its own unique signature. When hydrogen glows, it produces certain wavelengths of light. When carbon dioxide glows, it produces completely different wavelengths. Cyanide has its own pattern. Water vapor has another. It's like every chemical compound is singing its own song, and if you can listen carefully enough, you can identify exactly who's singing. This is what spectroscopy does. Astronomers take the light from a comet and spread it out into a rainbow using special instruments called spectrographs. Then they look for dark lines or bright lines in that rainbow. Each line is a fingerprint. Each fingerprint identifies a molecule. Put all the fingerprints together and you get the comet's chemical recipe. When the James Webb Space Telescope, the most advanced infrared observatory ever built, turned its golden mirrors toward 3IATLAS in August of 2025, scientists expected to read that recipe clearly, and they did find something extraordinary. The comet was releasing gases. Nickel and cyanide were detected, confirming that 3IATLAS was indeed a comet, actively sublimating as the sun warmed its surface. But more importantly, they found that extreme carbon dioxide enrichment we talked about earlier. 7.6 times more carbon dioxide compared to water than normal comets. That number jumped out like a flashing neon sign saying, "Something is different here." The spectroscopic data confirmed exactly what the models predicted. The gases coming off 3IATLAS weren't pristine materials from its birth star system. They were the product of billions of years of cosmic ray processing. That thick, irradiated crust, 15 to 20 meters deep, was now outgassing as the sun heated it. The light was revealing the history of transformation, not the history of origin. But here's where things got puzzling. Despite all that gas activity, despite clear evidence that the comet was sublimating and releasing material, white light images didn't show what astronomers expected to see. There was no obvious dust tail. Most comets develop beautiful sweeping tails made of dust, particles pushed away by sunlight. But 3IATLAS, its tail was ambiguous, faint, and in some observations, researchers noted evidence of an anti-tail, a strange feature pointing toward the sun instead of away from it. This is where the irradiated crust explains everything. Remember, carbon dioxide is highly volatile. It doesn't need much heat to turn from ice into gas. Water ice, on the other hand, needs more warmth. A comet dominated by carbon dioxide starts outgassing much farther from the sun than a water-dominated comet. And crucially, carbon dioxide outgassing is more efficient at releasing gas without kicking up much dust. Think of it like this. Imagine you have a frozen bottle of soda and a frozen bottle of water. As they warm up, the soda will start fizzing and releasing gas much earlier because of the dissolved carbon dioxide. The water just sits there until it melts. 3I Atlas is that soda bottle. Its carbon dioxide-rich crust started outgassing early and vigorously, creating a large gas cloud around the nucleus. But because the gas escaped so efficiently, it didn't need to drag much dust with it. Less dust means a fainter, harder-to-see tail. The anti-tail feature adds another layer of mystery. Anti-tails happen when we view a comet from a specific angle, and we're seeing larger dust particles that haven't been pushed far from the nucleus yet. They appear to point sunward, creating an optical illusion. The fact that 3I Atlas shows this feature suggests its dust is unusually large and heavy, another consequence of that process-it outer crust. So the light revealed a paradox. Spectroscopy screamed active comet, lots of gas. But images whispered, where's all the dust? The answer lies in that billion-year transformation. The comet's outer layers have been so fundamentally altered by galactic cosmic rays that even its outgassing behavior is different from normal comets. It's releasing the right gases, but in the wrong proportions, creating a visual appearance that doesn't match the chemical signature. This is the frustration and the beauty of studying interstellar visitors. You get one chance, the comet passes through, you gather as much data as possible, and then it's gone forever. And sometimes, like with 3IATLAS, the data you collect raises more questions than it answers. The spectroscopy confirmed the visitor is real, that it's a comet, that it carries the scars of an interstellar journey. But it also confirmed that we're not seeing the pristine materials from another star system. We're seeing what the galaxy did to those materials over billions of years. Even light keeps some secrets, and 3I Atlas, with its ambiguous tail and its extreme chemistry, is keeping plenty of them. But here's something that makes this story even more dramatic. Despite its billion-year journey through the galaxy, despite that protective radiation-damaged crust, 3IATLAS is fundamentally fragile. Comets, regardless of where they come from, are some of the most delicate objects in space. They're not solid rocks. They're more like cosmic snowballs held together by gravity, so weak it's almost non-existent. And when you bring a cosmic snowball close to the sun, things can go catastrophically wrong. Let's talk about what comets are actually made of. Imagine taking snow, dust, and frozen gases, mixing them together loosely, and then letting that mixture freeze solid in the deepest freezer you can imagine. That's a comet nucleus. But here's the crucial part. It's not packed tight. It's incredibly porous, filled with empty space like a frozen sponge. Scientists studying solar system comets have measured densities as low as 533 kilograms per cubic meter. That's less dense than freshly fallen snow on Earth. The porosity, the amount of empty space inside, can be as high as 72 to 74%. 3/4 of the comet is literally nothing, just empty gaps between ice particles. This makes comets incredibly weak. There's almost no strength holding them together. The gravity of something the size of Manhattan, which is roughly how big 3IATLAS is estimated to be, is pathetically small. You could literally jump off its surface and float away into space. The only thing keeping the comet in one piece is that weak gravity and some minor cohesion between ice grains. That's it. No structural integrity whatsoever. Now imagine bringing this fragile, porous, loosely held together ice ball close to the sun. At 3I Atlas's closest approach, on October 29th, 2025, it came within 1.36 astronomical units of our star. That's about 127 million miles, roughly the same distance as Earth orbits. That might sound far, but for a comet, it's close enough for the sun's heat to cause serious problems. Here's what happens. Solar radiation warms the surface. Ice doesn't melt in space because there's no air pressure. Instead, it sublimates, turning directly from solid to gas. Water ice, carbon dioxide ice, carbon monoxide ice, all of them start turning into gas and escaping. This creates pressure inside the porous nucleus. Gas builds up in the tiny spaces between particles, pushing outward. Eventually, that pressure finds weak points and erupts as jets, powerful streams of gas shooting out from specific spots on the surface. These jets are not gentle, They're violent releases of pent-up pressure. And because the comet is rotating, those jets create torque, like tiny rocket engines firing in different directions. The comet starts spinning differently. The jets push against the weak structure. And remember, there's almost nothing holding this thing together. The centrifugal force from rotation combined with the violent outgassing can literally tear the comet apart. And here's where 3I Atlas extreme carbon dioxide enrichment makes everything worse. Carbon dioxide is highly volatile. It sublimates much easier than water ice. That means 3I Atlas started outgassing early and aggressively. The jets were powerful, the pressure was intense, and the strain on the already ultra-weak structure was enormous. This comet was basically trying to hold itself together while internally exploding with gas. We've seen this destruction before. In fact, there's a warning written in the sky. Comet C 2019 Y4, discovered by the same Atlas survey that found 3I Atlas, spectacularly disintegrated in April 2020. It was heading toward perihelion when suddenly it started breaking apart. The Hubble Space Telescope captured images showing the nucleus crumbling into more than 30 separate fragments. Each fragment continued outgassing, creating a cascade of smaller mini-comets, all doomed. Within weeks, what was once a single comet was a cloud of debris. The breakup exposed fresh, pristine ice that had been buried inside the nucleus. This newly exposed ice sublimated furiously, releasing compounds like cyanogen in intense bursts. For a brief moment, the dying comet blazed brighter than it ever had when intact. Then the fragments dispersed, and it faded from view forever, a heart of snow that could not survive the sun's glance. 3I Atlas faced the same risks. Its ultra-porous structure, its violent carbon dioxide outgassing, its weak self-gravity, all of it made fragmentation a real possibility. Scientists watching it approach perihelion were genuinely uncertain whether it would survive. Some models suggested the thermal stress and outgassing forces could overwhelm the structural integrity. The comet could break apart just like C 2019 Y4 did, scattering into fragments that would quickly evaporate. As October 29th approached, observations became more frequent. Astronomers watched for signs of distress, changes in brightness, sudden bursts of activity, anything indicating structural failure. The comet did show unusual behavior, including that mysterious anti-tail and fluctuating brightness. For a while, it was unclear whether 3IA TLAS would hold together or crumble under the sun's thermal assault. The comet survived perihelion intact, but the risk was real. Even now, as it speeds away from the sun at over 150,000 miles per hour, it's still outgassing, still under stress, still vulnerable. It won't truly be safe until it's far enough from the sun that the heat can no longer drive sublimation. Only then will the jets stop, the pressure ease, and the fragile structure stabilize. This is the paradox of interstellar visitors. They cross billions of miles of empty space, endure eons of cosmic ray bombardment, survive collisions with interstellar dust, only to face their greatest danger in the few weeks they spend near a star. The sun's warmth, the very thing that makes the comet visible and scientifically interesting, is also the thing most likely to destroy it. 3I Atlas survived perihelion. On October 29th, 2025, it swung around the sun at 126 million miles away, moving at its maximum speed of 68 kilometers per second, and it held together. The fragile comet endured the thermal stress, the violent outgassing, the gravitational tugs, and now it's leaving. Forever, because that's what the mathematics demands. Let's talk about the beautiful inevitability of celestial mechanics. When 3I Atlas entered our solar system, it brought with it a specific amount of energy, encoded in its velocity and trajectory. That energy determined everything. The sun's gravity pulled on the comet, bending its path, accelerating it as it fell inward, then slowing it as it climbed back outward. But here's the crucial point. Gravity can change the comet's direction and speed, but it cannot change the fundamental nature of its orbit. A hyperbolic trajectory with positive orbital energy stays hyperbolic. The equations are absolute. Departure is guaranteed. Think of it like rolling a ball up a hill. If you don't roll it hard enough, it climbs partway up, stops, and rolls back down. That's an elliptical orbit, bound to return. But if you roll it fast enough, it crests the hill and keeps going down the other side, never returning. That's a hyperbolic orbit. Once the ball has enough speed to clear the hill, nothing can bring it back. 3I Atlas cleared that gravitational hill by an enormous margin. It didn't just barely escape. It rocketed over the threshold with tremendous excess velocity. The hyperbolic excess velocity of 58 kilometers per second is the key number here. This is the speed 3I Atlas would have infinitely far from the sun, after gravity has done everything it can to slow the comet down. Even at infinite distance, 3I Atlas will still be moving at 58 kilometers per second. That's its permanent, unshakable speed, the velocity it carried from its home system and will carry into the next part of the galaxy. But wait, you might think, what about Jupiter? Jupiter is massive. It's 2.5 times more massive than all the other planets combined. Its gravity is so powerful that we use it as a slingshot to send spacecraft to the outer solar system. Surely Jupiter could capture 3I Atlas, or at least significantly change its path. The analysis shows that while 3I Atlas passed relatively close to Jupiter's orbit, with a minimum orbital intersection distance of about 0.2.5 astronomical units, Jupiter's gravitational influence resulted in only a minor perturbation. The comet's trajectory bent slightly, changing by a fraction of a degree. But that enormous hyperbolic excess velocity meant Jupiter's gravity couldn't do anything more than nudge the path. To actually capture 3I Atlas and turn its hyperbolic orbit into an elliptical one would require removing an impossible amount of kinetic energy. Think about what capture means. You'd need to slow the comet down from 68 kilometers per second to less than 42 kilometers per second, the escape velocity. That's a change of more than 26 kilometers per second. A simple gravitational flyby cannot do that. Gravity can redirect motion, but it cannot destroy kinetic energy. When a spacecraft uses Jupiter for a gravitational assist, like Pioneer 10 did in 1973 to eventually leave the solar system, the spacecraft gains speed by essentially stealing a tiny bit of Jupiter's orbital momentum. But it's a trade. Jupiter slows down imperceptibly. The spacecraft speeds up. The total energy of the system is conserved. For Jupiter to capture 3I Atlas, the comet would need to collide with something, like a moon or Jupiter itself, dissipating energy through impact, or it would need to experience enormous drag from passing through Jupiter's atmosphere. Neither happened. 3I Atlas sailed past Jupiter's orbit, felt the planet's gravitational tug, curved slightly, and continued on its way. The laws of physics permit no other outcome. This is the triumph of mathematics over local circumstances. Yes, the solar system is filled with massive bodies. Yes, they all pulled on 3I Atlas as it passed through. The Sun pulled hardest. Jupiter added its influence. Mars and Earth contributed their tiny gravitational nudges. Every atom of mass in the solar system exerted some minuscule force on the comet, and all of those forces together still couldn't overcome the simple mathematical fact that 3I Atlas arrived with positive orbital energy and must leave with positive orbital energy. Conservation of energy is not negotiable. As of November 9th, 2025, 3I Atlas reappeared in Earth's sky after passing behind the Sun, now visible low on the eastern horizon before dawn near the constellation Sagittarius. Its magnitude 9.8, far too faint for the naked eye, requiring a telescope at least 8 inches in diameter to see. The comet is already speeding away at over 150,000 miles per hour, heading back into interstellar space. Its solar elongation, the angle between the comet and the Sun as seen from Earth, is increasing. Every day it gets a little farther away. Every day the Sun's influence weakens slightly. But even now, months from perihelion, its departure velocity is barely changing because it's still so close to its hyperbolic excess velocity. The trajectory of 3I Atlas is a perfect demonstration of gravity's silent obedience to mathematical law. The comet did not choose to leave. It had no agency in the matter. The numbers determined everything. Eccentricity greater than 1 equals permanent departure. Velocity greater than escape velocity equals freedom from gravitational binding. There is no ambiguity, no uncertainty, no possibility of return. The mathematics spoke, and reality obeyed. And there's something profoundly beautiful in that certainty. In a universe full of chaos and randomness, where quantum mechanics tells us that particles can be in multiple places simultaneously, and where the future is fundamentally unpredictable, celestial mechanics offers absolute clarity. Give me an object's position and velocity, and I can tell you where it will be 1,000,000 years from now. The equations predict loss as beautifully as they predict arrival. 3I Atlas came, curved, and departed, following a path drawn by gravity's math with perfect precision. Someday, thousands of years from now, 3I Atlas will be so far away that the Sun will be just another dim star in its sky, and it will still be moving at 58 kilometers per second, carrying the memory of its brief visit to our solar system in its trajectory forever. So 3I Atlas is leaving, following its mathematically predetermined path back into the galaxy. But before we say goodbye to this visitor, we need to talk about what it's carrying, because hidden within that radiation-damaged crust, beneath those layers of processed ice and organic tar, is something profoundly important. This comet is carrying the building blocks of life, and not just any building blocks, the same ones that seeded Earth billions of years ago. Let's step back and think about what comets actually are in the grand story of the universe. They're not just dirty snowballs wandering through space. They're time capsules. They're delivery vehicles. They're frozen libraries containing the chemical recipe for planets and, potentially, for life itself. When stars form, They're surrounded by enormous clouds of gas and dust. These clouds, called molecular clouds, are incredibly cold, just a few degrees above absolute zero. At those temperatures, gases freeze solid onto tiny dust particles, forming icy mantles. Water ice is the most common, but there's also carbon monoxide, carbon dioxide, methane, ammonia, and dozens of other simple molecules. These icy grains stick together, building up into larger clumps and eventually into comets and asteroids. The comets preserve those original ices like frozen records of what the birth cloud contained. But here's the truly amazing part. Those molecular clouds don't just passively collect molecules, they create them. The same cosmic rays and ultraviolet radiation that damaged 3I Atlas during its interstellar journey also drive chemistry inside these clouds. A high-energy radiation breaks apart simple molecules and creates reactive fragments called radicals. These radicals combine in new ways, building complex organic molecules, alcohols like methanol, aldehydes like formaldehyde, acids like formic acid, even amino acid precursors like hydrogen cyanide, which was detected coming off 3I Atlas at rates of several kilograms per second in September 2025. Think about what that means. Hydrogen cyanide sounds toxic and dangerous, and it is if you breathe it. But in space chemistry, it's incredibly important. It's one of the key ingredients for making amino acids, the building blocks of proteins, which are essential for all life on Earth. When you mix hydrogen cyanide with water and a few other simple compounds, expose them to energy, and give them time, you get amino acids. Scientists have done this in laboratories, recreating the conditions of space and successfully synthesizing biological precursors. And 3I Atlas is releasing hydrogen cyanide. Right now, as it speeds away from the sun, it's venting this crucial prebiotic compound into space. The same compound that probably helped start life on Earth billions of years ago. The same chemistry happening on a comet from another star system. This is where the story becomes deeply emotional, because what 3I Atlas proves is that the chemistry of life is not unique to our solar system. The same processes that created the organic molecules on Earth's surface 4 billion years ago are happening around other stars. The same radiation-driven synthesis, the same freezing of volatiles onto dust grains, the same preservation in comets, the same delivery to planets. When astronomers study the spectra of comets, they find methanol, formaldehyde, ethanol, glycolaldehyde, and many other organic molecules. These aren't rare or unusual. They're common. We've detected them in comets throughout the solar system. We've detected them in molecular clouds across the galaxy. And now, with 3I Atlas, we've confirmed them on an object that definitively came from somewhere else. The frozen alphabet of life, as the original document poetically called it, is universal. This means that when planetary systems form around other stars, they're being seeded with the same chemical ingredients that Earth received. Billions of comets, each carrying water, organics, and prebiotic molecules, bombarding young planets during their formation. Some of those planets will be in the habitable zone, the right distance from their star where liquid water can exist. Some will develop atmospheres. Some will have the right conditions for those simple organic molecules to combine into more complex structures. Some might develop chemistry complex enough to replicate itself. Some might develop life. We don't know if life exists elsewhere, but 3i Atlas tells us that the chemistry required for life is not special. It's not rare. It's not a cosmic accident that only happened once in our solar system. It's a natural consequence of how stars form, how molecules behave in cold, irradiated environments, and how planetary systems assemble themselves from clouds of gas and dust. Perhaps, somewhere, under another sun, on a planet we'll never see, orbiting a star whose light will never reach Earth in any human lifetime, life began from the same frozen alphabet, the same methanol, the same formaldehyde, the same hydrogen cyanide, delivered by comets chemically identical to the ones that bombarded early Earth. Life that might be asking the same questions we are. Life that might be studying its own interstellar visitors and reaching the same conclusion. We are not alone in chemistry. The building blocks are everywhere. The processes are universal. The delivery mechanisms are common. And 3i Atlas, with its cargo of organic molecules and its billion-year journey from another star, is living proof of cosmic kinship written in chemistry. This visitor came from somewhere. It formed in a cloud around a star we cannot identify. It was ejected by forces we can only guess at. It wandered for eons through the galactic void, and when we finally studied it, we found molecules that mirror the ones that started life here. Not alien chemistry, not exotic compounds requiring bizarre conditions, just the familiar universal chemistry of carbon, hydrogen, oxygen, and nitrogen, combining in the cold darkness between stars. That's the profound message carried by 3i Atlas. Life's ingredients are not unique. They're galactic. They're everywhere. And if they're everywhere, then perhaps life itself is not as rare as we once thought. Now here's the part of the story that shifts from individual wonder to collective awe, because 3i Atlas, as extraordinary as it is not alone. It's not even rare. Right now, as you read this, there are thousands of interstellar objects passing through our solar system. We just can't see them. Let that sink in for a moment. Thousands, not dozens, not hundreds, thousands of visitors from other star systems, silently cruising through the space between planets, completely invisible to us because they're too small, too dark, or moving too fast for our telescopes to catch them. We've only confirmed 3. 1i Oumuamua in 2017, 2i Borisov in 2019, and now 3i Atlas in 2025. 3 objects in 8 years. But statistical models tell us the real population is staggeringly larger. Let's talk numbers. Astronomers have calculated that the Milky Way galaxy contains somewhere around 10 to the 24th power interstellar objects. That's a 1 followed by 24 zeros. 10 septillion wandering pieces of debris, ejected from planetary systems across 200 billion stars, drifting through the galaxy like cosmic tumbleweed. Most are tiny, asteroid-sized or smaller. Some are comet-sized, like 3i Atlas. A few might be planet-sized, though we've never detected anything that large. Now focus down to just our local neighborhood. Statistical models suggest that at any given time there are roughly 10,000 interstellar objects the size of Oumuamua, which was a few hundred meters long, residing inside Neptune's orbit. 10,000 visitors, right here, right now, within the volume of space we consider our solar system, and we've found 3. Why so few? Because detecting these objects is incredibly difficult. They're moving fast. 3i Atlas was cruising at over 130,000 miles per hour when discovered, and accelerated to 152,000 miles per hour near the Sun. That means observation windows are fleeting. You might have days or weeks to spot the object, confirm its trajectory, and gather data before it fades from view forever. Miss that window, and it's gone. They're also faint. Most interstellar objects are small and dark. They don't reflect much sunlight. You need powerful telescopes capable of detecting sources dimmer than magnitude 24.5, which is about 10 million times fainter than what the human eye can see. Only the largest, most advanced survey telescopes can reach that sensitivity. And here's the challenge. You need both wide field of view and deep sensitivity simultaneously. Wide field to scan large sections of sky quickly because you don't know where the visitor will appear. Deep sensitivity to detect faint objects. But those two requirements usually conflict. Wide field telescopes sacrifice depth. Deep telescopes sacrifice coverage. It's like trying to find a specific grain of sand on a beach while wearing a microscope. You can see detail, but only in a tiny area. This means our current discovery rate is massively biased. We're only finding the biggest, brightest, most active objects. Comets like 2i Borisov and 3i Atlas that develop visible comas and tails, making them easier to spot. The smaller, dormant, asteroid-like interstellar visitors, they're passing through silently, completely invisible to us. We know they're there because the math demands it. When you work backward from galaxy-scale ejection rates and velocities, the numbers say thousands of objects must be transiting our neighborhood constantly. Think about what that means. Right now, somewhere beyond Neptune, an interstellar asteroid the size of a football field is silently crossing the outer solar system. Right now, a comet from a star system 50 light-years away is approaching Jupiter's orbit, invisible because it's too far from the Sun to develop a coma. Right now, debris ejected from a planetary system billions of years ago is passing between Earth and Mars, and we have no idea it's there. The galaxy is teeming with wanderers, and we're only seeing the tiniest fraction. This is where probability becomes poetry. We are not alone in motion. We are not isolated. We live in a galaxy thick with traffic, a cosmic ocean filled with travelers. Every star system contributes to this population. When planets form, gravitational interactions eject material. When stars pass close to each other, their gravity scatters comets and asteroids into interstellar space. Over billions of years, this process has populated the Milky Way with an invisible rain of debris. And that rain is falling through our solar system right now, constantly, silently, mostly unseen. 3 confirmed detections in 8 years. But beneath that tiny confirmed number lies the vast statistical reality. Thousands present, millions transiting over decades, billions over the lifetime of our solar system. We're not witnessing a rare event when we detect an interstellar visitor. We're witnessing our increasing ability to see what was always there. The universe is not empty. The space between stars is not a void. It's filled with remnants, with travelers, with pieces of other worlds carrying stories we can barely begin to read. 3i Atlas is one of those storytellers, bright enough and large enough for us to notice. But it represents a vast unseen population, the count of which transforms from dry statistics into something deeply moving when you realize what it means. We are not alone. We are surrounded. Every night, under a sky that appears static, interstellar objects are passing overhead. We just don't have the eyes to see them yet. But we will, and when those eyes open, when the next generation of telescopes comes online, we will finally see the rain that has been falling all along. So we know they're out there, thousands of interstellar visitors passing through silently, while we catch only the brightest few. But here's where the story shifts from what we've seen to what we're about to see, because humanity is building the tools to finally open our eyes to that invisible rain. And when those tools come online, everything changes. The detection of 3I Atlas wasn't luck. It was the result of a specific technological capability. The Atlas Survey Telescope in Rio Hurtado, Chile, scanning the sky repeatedly, looking for anything that moves. Atlas was designed to find asteroids that might threaten Earth, but its rapid cadence scanning makes it perfect for catching fast-moving interstellar visitors. On July 1st, 2025, Atlas spotted something moving quickly across the sky, just inside Jupiter's orbit at 4.5 astronomical units from the Sun. Within days, follow-up observations confirmed the hyperbolic trajectory. 3I Atlas was discovered because we were looking in the right place at the right time with the right tool. But Atlas is just the beginning. The real revolution is about to arrive. Its name is the Vera C. Rubin Observatory, and it's going to change everything. Imagine a telescope with an 8.4-meter mirror, one of the largest survey mirrors ever built, combined with a 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy. Now, imagine that telescope scanning the entire visible southern sky every 3 nights, over and over, year after year, going deeper and covering more area than any previous survey. That's the Rubin Observatory, and it's specifically designed to find things that move, change, or appear where nothing was before. The key to finding interstellar objects is cadence. You need to image the same patch of sky repeatedly and quickly. Compare one night's image to the next. Anything that moved is flagged. Most moving objects will be asteroids and comets from our own solar system, following predictable elliptical orbits. But occasionally, something will move differently. Too fast, wrong direction, trajectory that doesn't close. Those are the interstellar visitors. The Rubin Observatory's legacy survey of space and time, called LSST, will generate approximately 20 terabytes of data every single night. That's more data than a human could possibly analyze, which is where the second piece of the revolution comes in: artificial intelligence. Machine learning algorithms have been specifically trained to identify interstellar tracklets, those brief sequences of positions showing hyperbolic motion. Systems using gradient boosting machines and random forests can classify objects with 99.9% accuracy, instantly separating the rare interstellar visitor from millions of solar system objects. Conservative projections suggest that once LSST begins full operations, it will detect one interstellar object every few months. By the early 20s, we could have dozens of confirmed interstellar visitors. By the 20s, hundreds. The 3 we've found so far will look like the tiny beginning of a vast catalogue. And here's why that matters. Right now, we can't answer basic questions. How common are interstellar comets versus asteroids? Do most come from nearby star systems or from across the galaxy? Are their compositions similar to solar system objects or radically different? What percentage have been processed by cosmic rays like 3I Atlas? We can't answer these questions with a sample size of 3, but with dozens or hundreds, patterns will emerge. Statistics will replace speculation. We'll begin to understand the true nature of the interstellar population, but finding them is only the first step. The ultimate goal is to meet them, to send a spacecraft to intercept one of these visitors, fly alongside it, study it up close, maybe even collect a sample and bring it back to Earth. This isn't science fiction. The European Space Agency and JAXA are already building a mission called Comet Interceptor, scheduled to launch in 2029. The spacecraft will park itself at the Sun-Earth Lagrange Point 2, a gravitationally stable location about 1 million miles from Earth, and wait. When a suitable target appears, either a pristine long-period comet from the Oort cloud or an interstellar visitor, the spacecraft will leave its parking orbit and race to intercept. 3 years of endurance is planned. If no suitable target arrives during that time, mission planners could redirect Comet Interceptor toward a reachable interstellar object detected by LSST or other surveys. The mission would fly past the visitor, taking close-up images, measuring its composition, studying its surface, all while traveling at tens of kilometers per second to match the interloper's speed. This is the promise we're making to future generations. We're building the infrastructure to systematically detect, track, and study interstellar visitors. The Rubin Observatory scanning the sky every 3 nights, machine learning algorithms sorting millions of detections, global networks of follow-up telescopes confirming hyperbolic trajectories, space missions ready to intercept targets at short notice. This is humanity's commitment to exploration, written in steel and silicon and software. And it's not just about science. It's about a deeper human need to understand our place in the universe. Every interstellar visitor carries information from places we can never reach. Stars too distant, systems too faint, planets we'll never see. But their debris reaches us. Their comets and asteroids pass through our neighborhood, carrying physical samples from other worlds. If we can catch them, study them, understand them, we're reading messages written in ice and rock by processes happening across the galaxy. 3I Atlas will fade from view in the coming months, speeding away into the darkness at over 150,000 miles per hour, never to return. But its legacy remains. It proved that interstellar visitors are real, that they're scientifically valuable, that studying them reveals truths about planetary formation and chemistry that apply across the galaxy. And most importantly, it proved that we can detect them if we try hard enough. The future we will meet is one where interstellar visitors are routine, where their arrival is expected rather than surprising, where we greet each new wanderer before it fades. Someday we'll send a spacecraft to meet one of them in deep space, traveling alongside a messenger from another star. Someday we'll bring back samples from beyond the solar system, holding in our hands material that formed in another stellar nursery billions of years ago. That future is coming. The telescopes are being built, the algorithms are being trained, the missions are being planned. Science is making a promise to keep listening, to keep watching, to keep searching the sky for the next visitor. And when it arrives, we'll be ready.